Saintsman, we have lesson 9.3, which is similar right triangles for the next thing that we're doing in this chapter. So, first thing that we're going to discuss is we're going to take just any right triangle. I'm going to orient it in this way. There was a project that I've given out with chapter 8 typically, and it involves effectively this same triangle over and over. The same particular diagram where we're going to take this triangle ABC, where the right angle is here at C, and we're going to create, in this case, an altitude from the right angle to the hypotenuse, and we're going to call this intersection where that altitude intersects with line segment AB. We're going to call that point D. So what we have here is we have three similar triangles that have been formed. Those triangles are triangle ACB, which is going to be similar, right? Because we have three triangles. We have a small one right here, right? We have a medium-sized one right here, and then we have the entire triangle itself, which is the big guy, and that guy is going to be similar altogether. So ACB, the largest right triangle, which is similar to ADC, also similar to CDB. Now, it's not just because I feel like it, but again, we can prove this to ourselves, right? And it's pretty straightforward. If we take this ACB, for example, right? And then you have the right angle and you have angle B, okay? ADC, actually let's go back. Let's take ACB, right? The big triangle. We have this right angle C. Now remember, this angle is also going to be a right angle right here at angle ADC because it's a linear pair that's been formed with a right angle. So if one is right, the other one is right. That's one of our theorems. So again, utilizing logic that we've learned back in the first semester, utilizing and employing some of these theorems. Now, we have two right angles. So there was angle ACB and ADC, and then we have angle A, which both of those triangles share. Angle A, they share reflexively, right? Angle A congruent to itself. And therefore, these are similar. Those two first triangles listed are going to be congruent, or not congruent, similar through angle, right? Angle similarity. Same thing. We can complete the same exercise with ADC and CDB, right? So ADC, right angle, right? CDB, right angle. So then those are going to be those two. And then what else do they share? Well, we're not quite sure. So let's actually prove a different one. Let's prove ACB and CDB. And if we have proportionality there, right? Which we have CDB as a right angle, and then they both share angle B reflexively. So we know that this triangle right here and this triangle right here are both going to be similar through angle. Therefore, all three are going to have to be similar because it's proving that all three angles are going to be congruent within each of those respective triangles, because we have two of them that are congruent because we prove them as we prove that as such. So that's where we use the transitive property, right? Similarity from here to here, or and really congruence of their angles, which would also prove it to exist also for ADC, or for these two, right? And then for these two, therefore, ADC and CDB also, we're going to have the same relationship. Now, prove it, that's fine. Employing it, that's going to be actually, ironically, the part that's going to be a little bit more straightforward. So let's go ahead and take this triangle we have here. We have a right triangle. We have an altitude. This side is 4, this side is 3, and we need to find x. How do we do that? Well, we have a right triangle, correct? Meaning that a squared plus b squared is going to give us our c squared, right? So this entire hypotenuse right here is going to be equal to 5, right? Because 4 squared plus 3 squared, or 3 squared plus 4 squared, we did it earlier. Right? Or in this case, we're just going to write it as c squared. So 5 would be our solution. Now, what did we just learn? We learned that there's going to be proportionality. So we're going to have this hypotenuse, 5, right, to the short side, which is 3, will be equal to the hypotenuse, 4, right, to that short side, x. Okay? Take my cross product. 5x is going to be equal to 12. So x, in this case, will be equal to 12 over 5. And that's how we're going to find x in this case. All right. Let's do a little bit more. Grab another example real quick for us. We're also going to discuss geometric mean. Now, let's talk about what that is. There's two types of mean. You guys are used to the arithmetic mean, which is just the average, right? And when you take the arithmetic mean, what you do is you take the sum of numbers and it's divided by the number of numbers, right? When we do the midpoint, we actually take the average of the x's and the average of the y's, but we're only dealing with two things, right? So an average of two things we're going to divide by 2. The geometric mean is a little bit different. The geometric mean, we're going to take a square root of the product of two numbers. Okay? So let's do a couple of geometric mean examples. Like, so for example, the geometric mean of 4 and 9, okay? Well, what we do then is 4 times 9, which is 36, and then we need to take the square root of 36, which is equal to 6. So the geometric mean, it's going to be between 4 and 9, but closer to 4 than it is to 9, okay? If you didn't notice. So let's take another one of these. Your geometric mean of, let's say, 2 and 50, right? Well, 2 times 50 is 100, right? Square root of 100, not 106, that's what it looks like. It's just a poorly written 0. It's just 10. So it's between 2 and 10, of course, closer to the smaller number. If I asked you to find the geometric mean of 7 and 25, okay? Well, what's my answer here? 7 times 25, right? And then we're going to take a square root, and then I'm going to get 5 rad 7, and that's your answer, okay? Which, if you punch that into a calculator, it's going to be a little bit over 13, which should make sense, right? 5 rad 7 is closer to 7 than it is to 25, but it is between the two numbers. So that's kind of one of those number sense sort of things you can do to check your work. So what's nice here is that there's a relationship, and why we learn the geometric mean is it winds up being a shortcut for when we do the following. Okay, so let's say we have this triangle right here. And it's a right triangle, and we have an altitude. Okay, so on that hypotenuse, it's subdivided, right? What this does for us is the following, is that our geometric mean, the altitude, x, is the geometric mean of the subdivided hypotenuse. You know what that means? It means that x right here is going to be equal to the geometric mean of the numbers 10 and 4, which is going to be rad 40, right? 4 times 10, or 10 times 4 is 40, so rad 40, which when you simplify, right, you can take the 4, it's going to come out, square root of 4 is 2, so 2 rad 10, and that's your answer. All right, fairly straightforward on that one. So that's the big problem-solving thing that we've learned here. So let's do some examples just for fun here, just to make sure we can kind of get into the right problem solving state of mind. So let's take the following triangle, which is a right triangle. Okay, and I have this height h. This is 25. This is 60. And this entire side is 65. So how am I going to do this problem? Well, I'm going to need to, again, solve this like I did earlier, which I have three similar triangles, right? So I have a hypotenuse, which is going to be 65. Right? And the hypotenuse to the shortest leg is 25. Why do I care? Hypotenuse to short leg. And then again, I'm going to take, for this triangle right here, right? 60 is my hypotenuse. And h is my short leg. And then I'm going to take the cross product. My calculator seems to be missing right now. Oh, I found it. Excuse me, Steve. It's worth my time to, of course, pull my calculator out, because I've seen this happen on the most recent chapter with ratios, where some of you guys were just so dedicated to show off how great you are not at doing mental math calculations, or even just doing it by hand. I mean, why risk it? I'm just going to let the calculator do all the heavy lifting. So 65h is going to be equal to 25 times 60. Well, some of you guys are just going to, stare at it, right, and wait for me to write down the answer for you here as you're taking your notes. But you should punch this into your calculator and have 1,500, right? You'll divide both sides by 65. I don't know how you would do this on your own. I mean, I know how you would. It's just so much labor. I don't know why you would do it, right? What winds up being about equal to 23.1-ish. You can actually simplify this fraction. So it's, 1,500 divided by 5 and 65 divided by 5, which is going to be 300 over 13, which is a good answer, but it's about equal to 23.1-ish. All right? And that I would take rounded, but I'm really interested in this answer right here, this improper fraction. Okay. Let's do a geometric mean problem. Got two more examples for us today. Here's a right triangle. Here's an altitude. Do not be so dedicated to the orientation of a figure, right? I have 2, I have 5, I have y. Let's solve for y. Well, remember that altitude is going to be the geometric mean of those two segments, right? That are where the way that the hypotenuse is subdivided. So literally 2 times 5, take a square root. So rad 10. That's it. Okay? Remember, this is the geometric mean. All right, my last example for today. Similar figure. Then I have a right triangle, and I have an altitude to my hypotenuse, and I've subdivided 3 and 8. And I'm trying to find this figure y. Now, how would I do that? Well, let's figure out what this altitude or this height right here is, h. If I have that, couldn't I use the Pythagorean theorem, right? Because why not, right? That's one of our tools to figure out what y would be as the hypotenuse. So that h is going to be equal to the geometric mean, right, which is the square root of the product of 3 times 8, or rad 24, which is really 2 rad 6, right? Now, why would I actually simplify to 2 rad 6? I'm going to stick with rad 24 because I'm going to wind up employing this right here as a part of the Pythagorean theorem. 3 squared plus rad 24 squared, right? Which, remember, if you square root, we're going to be left with just the number inside, and that's going to give us c squared, which in this case, that hypotenuse is y. So we're going to have 9 plus 24, right? 3 squared is 9. The square root of 24 squared is just the number by itself is equal to y squared. 33 is equal to y squared. So when we solve for y, we take a square root of both sides, right? Square root, and we're going to wind up with rad 33 is y. So it's all in play. Every single problem-solving measure that we've been given. We have geometric mean. We have similarity, so we can set up ratios because if we have an altitude at a right triangle now, right? We have 3 similar triangles that we can distinguish. Moreover, we have still the Pythagorean theorem. And of course, don't forget about special right triangles. You could have a 45-45-90 or 30-60-90. All ways that we can solve these right triangles. Trying to do more with less. Or do as much as we can with the tools that we have to solve problems. Please complete your assignment on campus. Good luck.